Welcome back. Section P4, inverse functions, your favorite inverse functions. So today I want to talk about verifying one-to-one inverse functions, domain and range of an inverse function, the value of an inverse function, and the trig inverse functions, just a few of those. So let's start with verifying. If you recall the inverse function, we'll start with, I guess we could look at a graph of inverses, and it might spark a little bit of your memory. Say if we have a function that comes in, maybe a cubic, I guess, comes to mind. So then if we have the point xy there, then we can also go ahead and find the inverse function by replacing the x's with the y's and the y's with the x's. So the inverse function is going to come in something like this and then come out like this, so that we have the point also yx is going to be on that graph. Now, if you recall, we could draw in that line of y equals x, and it's going to be reflected across that line. And that's what makes an inverse with the function itself. So how can we verify that the inverse is a function? Well, if I take the composite function of the function with its inverse, or the inverse with the function, then I will get the value of x out. Look, y equals x, we end up with x. So that's what we're going to end up with. So can we verify that these are inverses? So if f of x is x minus 3, g of x is x plus 3, we haven't identified this as f inverse yet because we don't know if they're inverses. We just have two functions. So we're going to go ahead and find the composite of these two functions. So we're going to find f of g of x. Remember, f of g of x asks us to take the g function and replace it with the x's in the f function. So that gives us x plus 3 minus 3. Notice I replaced my x's with x plus 3. To simplify that, x plus 3 minus 3 gives us x. And generally that's going to be enough, but we want to go ahead and do the proof of it. And remember, the proof of it asks us to find g of f of x as well. So we're going to take the f function and replace it with the x's in our g function. So we have x minus 3 plus 3 is going to end up with x as well. So this is going to verify that f of x and g of x are actually inverse functions of each other. In order to find the inverse function of a function, we replace the x's with the y's with the x's, and then we solve for y. So if here's our function f of x equals x squared plus 1, we can rewrite that as y equals x squared plus 1. Replace your x's in your y's, so x equals y squared plus 1. And we can go ahead and solve for y. So we're going to subtract 1. So we get x minus 1 equals y squared. Done, do a square. We're going to take the square root of that. Remember though, when we take the square root, we also have the plus or minus symbol that we give it, because it can be both the positive or the negative. And that gives us the inverse function. Now we could go back and test to make sure that these are the inverse is a function or not. We'll talk about that here in a second. Because we're going to go to the one-to-one, where a function and its inverse is a function as well. So if a function's inverse is a function, then the original function is going to pass the horizontal line test. So notice here I have two graphs, I have two functions, f of x, which is a linear function, negative slope, and it doesn't matter where we draw a horizontal line, we're only going to touch it in one place. So that's going to tell us that the inverse is a function as well. However, if, in this case g of x, we have a horizontal line, we can touch it in two places at this point in time. And it doesn't matter where on the graph, if we touch it in more than one place, then the entire function's inverse will not be a function. So in this case, our inverse is not a function. So that goes back to the one I just gave you, that example, that f of x equals x squared plus 1. Notice that graph there could resemble x squared plus 1, So we know that this does not pass the horizontal line test. So we know down here, this inverse is not going to be a function as well. So we cannot denote this as f inverse of x. We can just say that it's y equals. So that would be an example of where we may have a g of x function to denote the inverse of it. All right. So can we find, if we have f of x equals x minus 3, can we find f inverse of 1? Can we find the domain? Can we find the range? And hopefully we can with all of these, but let's go ahead and talk about them. To find f inverse of 1, several ways you can go about doing that. To start, if we're looking for f inverse of 1, we know that they're giving us the y value instead of the x value. So if I replace my y's with 1, that gives me x minus 3. I can go ahead and solve for x, so x is going to equal 4. The other way I could go about doing that would be actually finding the inverse of this function. So I could find my f inverse of x. In this case, if I replace my x's, I'd have x equals y minus 3. I would add 3 to both sides, so x plus 3 equals y. So my f inverse would be x plus 3. Then I can go ahead and find f inverse of 1. And f inverse of 1 would be 1 plus 3, or it would give me 4 as well. So either way, it doesn't matter. I'll also show you how to do it in a calculator, because we could have some problems where they're not easily found through algebraic reasoning. So how do I find the domain and how do I find the range? Well, hopefully, again, you remember that we would switch the x's with the y's with the x's. So if I switch the x's with the y's, my domain became the range. If I switch my y's with x's, my range becomes the domain. So we can say the domain of original function is going to equal the range of inverse function. And vice versa. The range of the original becomes the domain of the inverse. So if we come back up here to the original, so if I look at f of x, I know the domain, hopefully, we have a linear function, is negative infinity to infinity, and my range is negative infinity to infinity. So f inverse of x is going to be just switching those around. So my domain now is the range. Well, in this case, it was negative infinity to infinity, and my range was negative infinity to infinity as well, because that was the domain. Not a great example. Maybe I'll give you a different example here. Maybe we give you a g of x, and maybe I knew the domain of it was 0 to 3, and the range was maybe 4 to 7, non-inclusive. So then my inverse function, g inverse of x, my domain would be 4 to 7, and my range would be 0 to a 3 inclusive. Notice how my domain and my range, they just kind of flip-flop. So how does the calculator play in on this? Let me get a piece of paper here. I have to do a little add-on. So what if I gave you maybe f of x equals x squared plus 3x minus 5? And I ask you to find f inverse of 2, to say. Well, if I go about doing that, to find the inverse algebraically of this, kind of cumbersome. So if I go into replacing my 2 with f of x, so 2 is going to equal x squared plus 3x minus 5. We have a quadratic. I can go ahead and set it equal to 0, so I get x squared plus 3x minus 7. Well, how are you going to solve that? Well, that's where our calculator is going to come into play. So I'll pull the calculator up here. Hopefully you can see that. I'm going to go to y equals. I'm going to type in that equation. X squared plus 3x minus 7. And if I graph it, there we are. And if we're looking for the zeros, remember we're looking to see where we cross the x-axis. So I can do a second calc. I can do a 0. Move my cursor. Again, you can type in numbers if you want, or we can just move that little spider. I call it the spider. Sorry if you don't like spiders. So my 0 is at negative 4.541. I also have one over here, so I can go ahead and again do that second calc, do my trace, zeros, move my spider. This time I'm going to type in negative 1. I know it's on the left side. I'm also going to type in 3 for my right side, and then I'm going to hit enter. So I end up with a 1.541. And those are going to be my two values, or my two zeros. So that would be my f inverse of 2. There would be two values for f inverse of 2. So hopefully that gives you an idea of a couple of things you're going to see. Inverse trig, oh, your favorite. So with inverse trig, let's go ahead and talk about your domains, your ranges, and what the graph looks like. I'm not going to talk a whole lot about them, but here is the arc sine. Comes up here like this. We denote it as sine to the negative first of x. Domain is negative 1 to 1 inclusively. Range negative pi over 2 to pi over 2. So domain and my range. Arc cosine is going to look similar to that. Again, we talked about these last year. You can pause if you need to take a look at those. Here's our arctangent curve. Domain and the range as well. So how do we find the sine of the arc cosine of x? Hopefully, again, I'm very hopeful today, and I feel like I'm saying hopefully you remember, hopefully you remember, hopefully you remember. So the arc cosine of x, we can let that equal theta, because whenever we take the sine of anything, that's going to be an angle measure. So we're looking at theta equaling the arc cosine of x. We can solve for x by taking and undoing that arc cosine. If we think about what undoes an arc cosine, that would be the cosine. So if I take the cosine of the arc cosine, I'm going to go ahead and write that out. Not that you have to. But if I take the cosine of the arc cosine, remember these are inverses of each other. Again, I'm hopeful, ain't I? So the cosine of the arc cosine of x is going to give me x. So I know the cosine of theta equals x. So I can draw a nice triangle, right triangle. Go back to right triangle trig. I can set theta to being either of the other angles. I know the cosine, hopefully, is the adjacent side over the hypotenuse side. So my adjacent side would be x. I can make that a fraction, putting it over 1. So I'm looking for, then, the sine of theta. The sine of theta is going to be the opposite over the hypotenuse. So how do I find that side? Well, I have a right triangle. So I know that a squared plus b squared is going to equal c squared. So I know x squared plus b squared equals 1 squared, or 1. So b squared is going to equal 1 minus x squared. Here's our 1 minus x squared. So I know the sine then of theta is going to equal 1 minus x squared divided by 1, or 1 minus x squared. The square root of that. All right, so we know then the sine of the arc cosine of x is going to equal the square root of 1 minus x squared. And I have one more. I know it's a little on the lengthy side today, but hopefully, they're all review and it's not taking you too long to get through them. So the cosine of the arctangent of 3/4. Again, we can let theta equal the arctangent of 3/4. Take the tangent this time of theta of both sides. So the tangent of theta equals 3/4. Tangent is opposite over adjacent. So again, we can draw a triangle if you wish. There's our theta. So our opposite is 3, our adjacent is 4. So we know we have a 3/4. Hopefully, you remember your perfect triples, your Pythagorean triples. So 3, 4, 5 is a perfect triangle. If not, you can go back here and do your a squared plus b squared equals c squared. So 3 squared plus 4 squared equals c squared. 3 squared, 9, 16 gives us 25 equals c squared, or 5 equals c. So then we're looking for the cosine of theta. The cosine of theta is the adjacent over the hypotenuse. So we get the cosine of theta equals 4/5. So the cosine of the arctangent of 3/4 is going to equal 4/5. And there you go. And hopefully you remember all those wonderful things and you're able to get through the lesson. Good luck.